Hello everyone. In this first part we will look at some basic descriptive statistics. So we have two main players in statistics, which is the population, which is the most important one. We want to know something about a population. And we have the sample, which is actually the information we have or that we can use in order to extract some knowledge or information about the population, right? And so using the sample to make claims about the population is known as inferential statistics, which is what we will look at in the second and the third part. But before we do that, I will refresh your memory about some basic descriptive statistics, right? And we will end with the notion of a confidence interval. And I believe, especially for science researchers, definitely also in biomedical sciences, a good understanding of what a confidence interval actually means, and actually also when to use a confidence interval is very important. So I think it's a good idea to repeat that. So let's start with the population. So as I just said, the population is actually the most important. That's what we want to know things about. It's known as the set of all the, we call those individuals. So the set of all the individuals about which we want to make some inferences, about which we want to make claims about, know things about, right? And so these inferences will be made about one or more variable. We call them random variables, right? And so these variables, they say something about an individual, right? Okay, so as an example, let's say that we are interested in some gene, so let's call it gene A. It's a gene that is apparent in mice. And let's say that we want to make some claims about the expression level of this gene, right? And so the population for this gene A is actually consists of all mice, right? So those are the individuals. We want to know something about gene A in all mice, okay? So it should be clear that we don't have access to the expression level of gene A in all mice. So we will have to limit the information that we can use to make claims, inferences about the population of all the mice, right? Now, it's important to understand that what we will do here in order to explain all these concepts behind the statistics is that we will act as if we do know the expression level of all the mice, right? So we're going to use code, Python code, and simulate the idea of actually knowing everything about the population, right? And then trying to infer that again using samples, and that will be made much more clear once we go through this course, okay? So the population. We can describe a population by what is known a probability density function, right? And so, as it's stated here, this is a function whose value at any given point on the x-axis can be interpreted as providing a relative likelihood that the value of the random variable would be equal to that point. So it provides some probability about the different values that a certain random variable can take, right? So to explain this further, I borrowed this image, this plot from Professor Clement, which actually shows a probability density function here in red, as you can see. And so now what we can do here is use this function to compute the probability that my random variable here, so this was this blood pressure variable here, has a value between 115 and 120. So 115 here, 120 there. And so we can use this function, this probability density function, to compute that probability, right? And this is actually basically equal to the area under the curve here, right? So the area under the curve ranging from 115 to 120, right? And so we can compute that by computing the integral of the function in the range 115 to 120. So if we assume that, and like I said, we're going to act as if we know everything about the population of this gene A expression level in mice. So one thing we assume, or that we know, is that it actually follows a nice normal distribution, right? So the probability density function will follow a nice Gaussian curve. It's bell-like shape, symmetric bell-like shape, Okay, and so mathematically you can define that function as I'm showing here, right? So this would be the probability density function for a normal distribution. You can see that we have next to x, which is the value of our random variable for which we want to know this probability about, we have two other variables here. So we have what is known as the variance here, so sigma squared, okay, and we have mu here, which is known as the mean, right? And I don't have to tell you, formula for mean is that we just sum all the values and divide by the number of values. So this big N here is the number of individuals in our population, so that would be the number of mice in the population. And we have also got the variance, which is actually computed by looking at the sum of the differences between the value and the mean, and we square these values, and then of course we divide by the number of individuals in the population. Okay, so here we can see a number of these probability density functions, so they're all normal distributions, so they all follow this formula here, but they have different values for the mu and the sigma squared, so for the mean and the variance, right? So for instance, you can see here that these blue, red, and let's say that it's yellow, they have the same mean, so they have the same center. That's what you can see here, while the green one has a mean which is smaller, so you can see a shift here. And of course the variance determines the spread of the bell shape that you can see here. So by having these two values, we have determined the full probability density function for a certain population. So what's the purpose of actually taking the square of the difference between the mean and the observed value when computing the variance? Okay, so that's what I'm going to try to show you in this small intermezzo. So let's say we have like 4 data points in our sample, right? And so values are 4, 4, minus 4, minus 4. So we have a mean here, right? Okay, that's the mean. And so if we compute variance, we would take the difference between 4 and the mean, so it would be this, 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 and this, right? So we sum those, well, we sum the square of those, that's the variance, but let's say we don't do that, okay? So let's say we compute the variance without squaring, but we will use the absolute value of the difference. So the difference here is 4 plus 4, difference here is also 4 because it's the absolute value of minus 4, and then we have 4 here, and then of course we divide that in this case. Since we're doing a statistic, we divide that by 3, so n minus 1, okay? So that would give us a value of 5.3. Now consider this sample, right? So intuitively you could say there's a much more spread here. The spread in this sample is higher than the spread here, and as I mentioned, the variance is a measure of the spread of the values of your random variable, okay? But if we would again not take the square and just take the absolute value, so we have 7, 1, minus 6, minus 2, and we divide it by 3, we would get an equal value of 5.3. So the variance of this data set would be the same as the variance of this data set, while intuitively we can see that there is more spread in this data set or in this sample than is in this sample, okay? And so if we would use its square instead of the absolute value, which would actually emphasize these bigger distances, so it would make these much larger compared to these, right? That's what we see here. Then we can see that the variance that we compute on this sample is much higher than the value that we compute on this, and this is intuitively so a much better representation of the spread of your of the values of your random variable. So the variance is a measure of spread of the random variable under investigation, right? And so a more intuitive measure of spread is known as the standard deviation, okay? And so this is basically just the square root of the variance, as you can see here, okay? But it has some intuitive meaning, so I can show that here. No, I can show that here, okay? So what you see here are 3 normal distributions, so they have the shape of this bell-like shape, symmetrical shape, and as we have seen, this shape is determined by its mean, so would be the center of the distribution, and also the variance, or in this case we can use the standard deviation. And so we know here the mean is 19, so we have our shape being symmetrical around 90, and the spread is has a standard deviation of 30, right? And so the meaning of that is that if you look here, so you can see here that this curve starts making a shift in the turn. So we go here in this curve, we go to another curve, right? So we call this point here where that changes the saddle point, right? And so the standard deviation is actually the distance from the saddle point to the mean of the distribution. So in this case we have 30 here. So that means that if you know the mean and you know the standard deviation, you can in your head make a picture of what this bell-like shape looks like for this particular random variable. Okay. And also very interesting fact is that if we look at this normal shaped curve here, okay, so we can look at standard deviations. That's what's showing here. So here we have the 0, so this would be one standard deviation from the mean, so the mean is 0, so we can see that that corresponds to the saddle point, so where this curve changes into this curve, so that would be one standard deviation from the mean, and we know that we have about 34.30% of all the values in there, right? Okay, so we know for a random variable, we know that if we know the standard deviation, that about 68% of its values fall within these two ranges, fall within the mean minus the standard deviation, the mean plus the standard deviation. We know that for two standard deviations, 95% have a value within these two standard deviations. Okay, so by knowing the standard deviation, you know you have a lot of information about your random variable. Of course, assuming that your random variable is normally distributed. Okay, so there are some other parameters that describe a population, and that's important maybe to mention that these descriptive statistics that describe a population are known as parameters. Okay, and so the median is also a very well known one. So the median value is the value where 50% of all the values of the random variable have a value lower than that value, and 50% have a value higher. So that would be this 50% here. Okay, there's also something called the quantiles. Right, so as shown here, the quantiles are cut points dividing the range of a probability density function, so that would be this one, into continuous intervals with equal probabilities, right? So a well-known quantile is the quartile. So in general we have q quantiles, so if we have 4 quantiles we call it a quartile. So in this case we have 4 subsets of the data, and each of those subsets contain nearly 25% of the values. Right? So the first quantile, known as this Q1, so for the first quantile, that value, from that value we know that 25% of the data has a value lower than this Q1. Okay, and then the second is the Q2, right? So in this case we know, if we have that value, then we know that 50% of the values of our random variable have a value lower than this Q2, so Q2 would be equal to the median. Okay, and the same way we have a Q3, which would correspond to 75% of the values. Okay, and we also have the notion of an interquartile range, which is simply defined as the difference between this Q3 and Q1. Right, and this, as we will see, is typically used in what we know as box plots. Okay, and then of course I was talking about the Q quantile. So the quartile is a 4 quantile. Okay, you can also have 100 quantiles, which we then know as percentiles. Right, and these are also shown here. So that's at the bottom. So we have this 1% percentile here, which means that 1% of our values of the random variable have a value lower than this particular 1% percentile. Okay, so that brings us to the sample. So remember, the population is what we don't know about, what we want to know things about, but we don't know. We only have access to a very small part of this population, which should be drawn at random, which we call the sample. Also remember that in this course we will act as if we do know the population. So don't get confused about that. In reality, we don't know the population, but here we will act as if we do know the population. So in this case, we really know the mean and the variance of the full population of all the individuals. Okay, so let's go to the sample. So, like I'm saying here, so we have only a very small subset of the population, which we call a sample, sometimes also referred to as a data set. So let's go back to our example. So we have our gene A expression levels in mice, and let's say that we know that the mean expression level in the full population is 0.26, and the standard deviation in the full population is 0.05. So again, now from these values you can already make a picture of what this shape looks like in your head based on the information that I just told you. Okay. So now let's use code and let's make such a sample, right? So we're going to use a Python library, NumPy, right? And so in NumPy you have some functions that actually mimic a probability density function, right? So in this case it's called, it's in the package normal, we have a function, in the package random we have this function normal here, which allows us to determine a certain probability density function, right? So we determine that by setting the location, so that's the same as the mean. So as I told you, the mean was 0.26. And we also have to specify the standard deviation here, which, as I mentioned, is 0.05. So by saying this code knows that we are talking about the probability density function with this mean and this variance. And what we want the code to do is sample n individuals. So our sample will consist of n randomly sampled individuals from this population. Okay, and we set n to 60. So now, before I can execute this code, I need to execute this first part of the code. So remember, this is done by doing Shift-Enter. And the first time you actually run a notebook on Google Collaboratory, you have to click the Run Anyway button. Don't care about the text. And so now we are ready to run this piece of code here. So, okay, I run this. And now we have a sample with 60 values, randomly sampled from a population with these mean and standard deviation. And I can show you that how that looks like. So we have our gene A sample, right? And so as you can see here, we just have a bunch of values here with a mean probably close to 0.26, right? So 60 values here. Let's delete that again. Okay. So a better way to describe this sample, or the values in this sample, next to the list that I just showed you, is known as a histogram. So we're going to visualize this sample, and it's actually a very trivial thing to do. You just take all the range of all, in our case, gene A expression values, and you just bin those. So you create bins of equal size, and then you just count the number of values that fall within each bin. Right? And so we can use this small piece of Python code here to plot such a histogram for our sample. So we have our gene A sample, which we sampled here from this population. And so we can execute this code, and that will plot this histogram. So now, instead of just having a list of 60 numbers, we have a much clearer view of which numbers are more frequent compared to other numbers, right? So you can see the bins here, right? And so this actually tells us how many of the values in our sample fall in this bin. So this bin will be value between 0.2 and 0.225, right? So that's what it's saying. So a sample, from the sample, we can also compute the mean, right? So we will use a different notation for that. So we use smaller letters when we talk about the sample. So that's also true for the number of points in our sample. And so the mean, again, we just sum the values and we divide by the number of values. And the variance also very similar, except here that we divide by n-1, which apparently gives a much better estimate of the variance than dividing just by by n, right? And so next to the histogram, there's another very popular way of visualizing or describing, we're talking about descriptive statistics, or describing the sample. So that would be the box plot here. So this is what such a box plot looks like. So I can maybe zoom that out a little bit. Oh, it's zooming in. So you can see that, right? So here we have our probability density function, and we have our standard deviations here. And so here we don't really use means or standard deviations. We typically refer to the middle of this box plot, or this stripe. It's not always in the middle, I have to correct that. So this vertical stripe that we have is the median of the values in your dataset. And then we have what I just explained, the quartiles, right? So we had the Q1, the Q2, which was the median, and we had the Q3, right? So here we know that between the Q3 and the Q1 we have 50% of our values, right? And then we have another 25% here, and we have another 25% here. So another popular way to describe a sample, the values in a sample, is through another graphical representation known as the box plot, or a box and whisker diagram. So you can see an example of that here, and I will try to zoom that in a little bit. No, it's not working anymore. Okay. So what you can see here, it's basically a graphical description of the probability distribution function. And so what you need for the box plot is the median value. So you know that the vertical stripe in the box plot is always the median value of the random variable. And then we create a box which represents Q1 here and Q3 here, right? So we know on this side here we have 25%, and on this side from here to here we have 75%. So that means that here again we have 25%, right? So we have 50% inside the box. 50% of our values fall between Q1 and Q3, so that's good to know. And then we have 25% of our values being lower than Q1 and 25% of our values being larger than Q3, right? And so you also have these things here. So they are the whiskers, so they are defined as in this case Q3 plus 1.5 times the interquartile range, so that's what this is. And here we have Q1 minus 1.5 times the interquartile range. And so the idea here is that by definition we say that any value of our random variable which is higher than this value here is an outlier, or lower than this value here is considered an outlier. It's not expected. We are not expected to see that under normal distribution examples. Okay, so that's the box plot would show this for your random variable, and it might also show some points here, which are the points considered outliers based on the formula that we have here. So now let's go back to our sample with gene A expression levels. Okay, so we can use NumPy again to compute the mean of this sample. Okay, so we just execute this code, and now we computed the mean of the sample. So what we can see is we know that the mean of the population was 0.26, right? And so here we can see that it's not exactly 0.26, so it's actually slightly higher than 0.26. Okay, so we can see that if we want to say something about the population using the sample, we need to take some uncertainty into account, right? And the uncertainty is actually implied by a limited sample size. So the sample size is typically going to be much smaller than the number of individuals in the population. And so because you have to make decisions based on that small part of information, you know that there is some sort of uncertainty with the decisions you make. Okay, and statistics is actually all about quantifying this uncertainty, trying to quantify how uncertain you actually are about a certain statement, right? And in order to do that, and that's important, you have to make assumptions about these populations, right? The population from which the samples are drawn. Okay, and so when you make these assumptions, actually, when you make the correct assumptions, that would allow you to quantify the uncertainty you have about certain statements. So for instance here, about how certain are we that this is actually the mean of the population. Okay, so to recap, we have now the mean and the variance of the population. So those are examples of parameters, as I explained to you. So parameters are summary measures of a population, and so they are fixed. So one population has one fixed parameter values. Okay. Now the sample mean and the variance, the sample variance, they are known as descriptive statistics. So these are statistics. We have parameters for the population, we have statistics for the sample, in this case descriptive statistics. And these, and that's important, they are variable summary measures, right? So they are not fixed. So one sample can have different values, can have a different value for the mean and another sample. Okay, and so I can show that here in the code. So what we're going to do here is we're going to do the same thing as we did here. So where we sampled 60 individuals from this population. Okay, so now we're going to do the exact same thing, but we're going to do it 100 times, right? And instead of sampling 60 individuals, we're going to sample 16 individuals. So that's what we're doing here, doing the sampling. We can see that we're sampling from the same distribution, from the same population, I'm sorry. So the population with the mean 0.26 and with the standard deviation 0.05. So all of these 100 samples that I'm randomly drawing from that population, right? So each sample contains 16 points. So all of those are drawn from the same population, okay? And so what we're going to do is we're going to compute, or we're going to draw the sample at random, and then we're going to store in a list the sample mean, right? So for each sample that we draw, we're going to compute the sample mean, that's what you see here, right? And we're going to add that to this list called sample means. So let's do that, let's execute this code. So we have done that, and now we can plot these sample means. So we now have 100 sample means. I can show you that actually. So we have the sample means. Right, so that's a list of 100 sample means. Okay, and so again, we can give a better description of this list by maybe using a histogram. So that's what I'm doing here. So now I have the histogram of all the sample means. So again, we know that each sample is drawn from the same population, which has a fixed mean of 0.26. Yet you can see some variation in the sample means. So many of them will be centered around 0.26 because that's the population mean. But if you're unlucky here, you have one which actually has a mean of 0.23, or let's say slightly higher than that, or it can go up close to 0.29. So that's very different from this 0.26. So it means that depending on which sample you draw, you get a different estimate of the mean of the population. If you would use the mean of the sample to estimate the mean of the population, you would get different estimations depending on the sample you were drawn. Right? And again, it's very important to understand that in the real situation, you only have one sample. Right? So here I'm simulating drawing 100 samples and showing you the difference between those samples, but in reality you only have one sample, and it's going to typically be a very small sample with a small number of points in there. Okay, so again, if you're unlucky, you have this sample, you don't know, or you could have this sample. Okay, so now of course we can compute the mean of these means, so that would be the mean of all these values, and as we would hope to see, this would get very close to the actual population mean, right? And in fact, I mean, it speaks for itself. If we don't just draw 100 samples, but let's say we take 200,000 of them, as I'm going to do here. So I'm going to execute the same code, but instead of sampling 100 samples, I'm going to sample 200,000 of them, and then I'm going to compute the mean of these sample means. So that's what I'm doing now. And you can see that we're getting really, really close to the actual mean of the population, right? So that brings us to the confidence interval, which is the way to describe, so we're still doing descriptive statistics, to describe the uncertainty. So how uncertain or how certain are we about a certain statement, a certain claim. So in our case, we were looking at the mean of the population, so we estimated that from the mean of the sample. Okay, we saw a difference there, so then we want to know, because in reality we don't know the mean of the population, so we want to know the mean of the sample. How certain are we that this is the mean of the population as well? Okay, and so that's described by this confidence interval, and you don't have, it's not just for means, you can have confidence interval for all kinds of descriptive statistics. Okay, so just like we did here, so as you can see, we had these 200,000 samples that we randomly drew from the same population. Okay, and now we computed the mean of those samples. We can also compute the standard deviation of those sample means. Okay, so that's what you see here, that's the value. And so from that standard deviation, we can actually draw some conclusions about the uncertainty about the mean in this case. So let's first define what is known as the standard error of the mean, the SEM. Okay, oh, that was not the idea. So suppose we are able to draw all possible samples. So here we only drew 200,000. Okay, so suppose we are able to draw all possible samples with some fixed sample size n, which is 16 in our case. So in that case, given again the assumption of normality, then the standard deviation of the sample means, right, so that's what we have here, except that that would be all the sample means, is known as the standard error of the mean, right? And the standard error of the mean is equal to the standard deviation of the population, which we do not know, right? Well, we know them, but in reality you don't know this. So it's equal to the standard deviation of the population divided by the square root of the sample size n. And n is known, so that we can compute. Okay. And so I can show you here, we have in fact the actual standard deviation of the population, which we act as if we know it, so it's 0.05. And then we divide that by the square root of n, and then we get this value 0.25, which is indeed very close to this estimated value, because we only have 200,000 here, and the sum is only valid if we can have all of them. However, like I mentioned, we don't have all of these samples. In reality, we will only have one sample, and so we can make an estimate for the standard error of the mean by taking the standard deviation of that sample and dividing it by the square root of n. Okay, so given the sample, we can compute the mean, we can compute the standard deviation, and we can compute the standard error of the mean, right? Defined as I'm showing here. So now, in order to compute a confidence interval, we will make use of this. So in this case, we will compute the confidence interval of the mean of a population, right? So we use the sample to estimate the mean of the population, and we want to have some description of how certain we are about that mean, right? And we will do that by constructing a confidence interval. And a confidence interval is an interval of values computed from the sample, of course, that is almost true or almost sure, and so set by some level of confidence. So we could say we want to be 99% sure, we want to be 95, or we want to be only 80% sure. It's up to you. So it's your level of confidence. So it's almost sure to cover the true population value. So in our case, to cover the true population mean. Okay. So for instance, if we have a level of confidence of 95%, the confidence interval of the mean of a population is an interval of values computed from a sample drawn from this population, right, that is 95% sure to cover the true population mean. Okay, and I will show that with some code in a minute. First, we will actually here show how the confidence interval is actually computed. And so what we do here is we need the mean of the sample. So that's what we see there. We also compute the standard error of the mean. I'll show you the formula here. Right, and then we have our interval with the lowest value being the mean minus this standard error of the mean and the mean plus, where standard error of the mean is corrected with what is known a t-statistic. A t-statistic that follows some t-distribution with n-1 degrees of freedom. Now, I'm not going to go into that here, but I will go into these statistics and these t-distributions and this number of degrees of freedom in part 2 and part 3 of this section. Okay. So, how do we determine this t? Well, actually, just like in old time, we can go look it up in a book, right? So these are these typical critical values.
in this case for t. So what we would need here, so like we mentioned, we have n minus 1 degrees of freedom. So n would be the number of points, so the sample size. So it would be sample size minus 1. And that's what we have here, the domains of freedom. So here we have values for t for different sample sizes. Okay. And here we also have this level of confidence that we wanted the confidence interval to have. So let's say that's 99%. And then we can look up here depending. So we had like 16. Let's say we have 16, and I would go for the 15. So that would be my value for t that I would use here, right? So that's how you compute this confidence interval. And so now we can simulate that with some Python code here. So what I have here, and you don't need to, this is pretty cryptic coding, so you don't need to understand exactly what's going on here. But what it is a function, ci mean, which will compute the confidence interval. So it will return the confidence interval for some sample x. So this would be a list of values. And of course, we also need to know the confidence, because we need to know the confidence to get these t-statistic values, right? So let's say the confidence here, we want the confidence interval by default of 95%. Okay. And so what it will return, as you can see here, so it will return the mean of the sample. So it's actually computed here. And then the confidence interval. So this would be the lower bound of the interval, and this would be the upper bound of the interval. Okay, and now we're going to do some simulations. So that's what I'm showing in the code here. So let's first define this function. And so we're going to keep the confidence at 95%. Again, these notebooks are interactive. You can play with these values and see what happens for yourself, but let's stick to 95% in this case. So again, we're going to simulate drawing more than one sample. In reality, we only have one sample, but now we're going to pretend that we have like 1,000 samples, okay? And each sample has a sample size equal to 16, okay? And so what we're going to do for each of those samples, that's what I'm showing you here. So for each of those samples, we're going to compute the confidence interval. So that's this function that I defined here. So this will return the middle point, so the mean, and then the lower and the upper limits of the confidence interval, right? And then I'm going to check whether this confidence interval contains the actual true mean, because we know the true mean again is 0.26. Reality, we don't know this, but now we know this, right? So that's what we do here. We check whether this confidence interval that we computed from the sample here actually contains the true mean, right? And if it doesn't, that's what it checks here, then we add this to the number of wrong. So in this case, the confidence interval did not contain the true mean, the true population mean. Now, since we have put the confidence of our confidence interval to 95%, we expect this to see in 5% of the cases. Right? So in 5% of the cases, we will have a confidence interval that does not contain the true population mean. So let's run that. Okay, and so what it computed here, so it actually returns the 100 minus the number of wrong. So we expect to see 95% of the confidence intervals actually do contain the true population mean, and we can see that it's indeed very close to 95%. Right? So based on the assumptions that we made, being it the normal distribution of the normal shape of the population, and the assumptions that we made here seem to be correct if we simulate them, in this case for 1,000 randomly drawn samples from the same population. So an important message I want to bring here is that when you report descriptive statistics, like what is the mean, what is the variance, it is always a very good idea to also add the description of the uncertainty or the certainty that you have about that description. So for instance, that example that I show you here, when you write down or you provide the mean of some sample, it makes a lot of sense to also show the confidence interval, to put next to that the confidence interval. That gives you a lot more information about the uncertainty that we have of that one particular statistic, the mean.